Thank you all for coming. I am very pleased to introduce Professor Raja GuhaThakurta. He's a professor of astronomy at UC Santa Cruz, and he's an expert on galaxy formation and on Andromeda, and he's going to give us a talk about our place in the cosmos today. He's also started an innovative program for high school students to do research at UC Santa Cruz in the summer, and he's going to talk a little bit about that towards the end of the talk. So I'm thrilled to introduce Raja.
Thanks a lot, Jeff, and thanks, Boris. Can you hear me okay at the back there? Okay, great. And thank you both for setting this up. In fact, the high school program that Jeff mentioned is the exact reason for my connection to Jeff. His daughter is in this program. So I'm going to talk about that at the very end. And I see a bunch of high school students. I see a bunch of middle school students here, right? Middle or elementary? Elementary, even better. Good to start early. So I'm going to talk about galaxies today. But I want to explain why it's important to talk about galaxies. I'm going to explain why I study galaxies. And so the title of today's talk is Our Place in the Cosmos. And what I want to do is explain why, why galaxies have any connection at all to you and me. By way of giving credit where it's due, many of the slides you'll see today, most of the narrative you'll see today, was put together with the help of one of my colleagues at the UC Santa Cruz Astronomy Department. Her name is Sandra Faber. Sandy has been studying galaxies for 30 years. She's one of the world's experts in the study of galaxy formation and evolution. So I've had the privilege of working with her. We've worked together to keep this narrative current. As the years have gone by, we've adapted our story to new findings. We've adapted the images and animations to new findings. So I hope to give you a little bit of a tiny flavor of the kind of galaxy research that goes on at Santa Cruz and around the world. So I wanted to put in a little bit of a disclaimer also that astronomy and cosmology are often confused with astrology, gastronomy, and cosmetology. And I just want to set those three topics aside. They actually rear their ugly head more often than I care in my study, especially when people find out I'm from India and I study astronomy. I always get asked about palmistry and telling the future. I know absolutely nothing about astrology. I know a little bit about gastronomy. It keeps me alive. And I know as you can tell, looking at me, I know nothing about cosmetology at all. But where they do rear their ugly head, I'll mention them. But this is a good example of cosmetology rearing its ugly head. No pun intended. So let me actually give you a little bit of a roadmap of where we're going to go with this narrative today. So I'll start with our place in the universe, in the cosmos, and it turns out our place in the cosmos is directly linked to a concept that's best thought of as recycling. Recycling of chemicals, recycling of the elements in the periodic table, but done by the cosmos, not done by West Valley recycling. It's done on a much larger scale in the cosmos, and it's done inside galaxies. Galaxies are the cosmos's recycling plants. Now, galaxies do a whole bunch of things in addition to cosmic recycling. They are also cannibals. They like to eat their own. They like to eat their children in particular. So nothing to be scared about, you kids. Your parents are not at all like that. But galaxies, in fact, do this all the time. And I'll talk about how cannibalism plays an important role in galaxies. So you can see gastronomy is already rearing its ugly head here. The formation of galaxies involves cannibalism, but only in the late stages of galaxy evolution. Today, there's a lot of cannibalism going on in the Milky Way, in Andromeda, but in the early stages, you don't have cannibalism because there's nothing to cannibalize. You need to have galaxies in place for them to cannibalize one another. So the early stages of galaxy formation actually involve other processes, and I'll talk a little bit about that. The early formation of galaxies involves ripples in the fabric of the cosmos. I'll talk a little bit about the processes that give rise to those ripples. It has to do with quantum mechanics, has to do with a phenomenon called inflation, not the economic kind, but the kind the universe does, and it has to do with gravity. So I'll talk about those things. And near the end of the science part of the presentation, what I want to emphasize is that astronomy is a physical science, so like everything in the sciences, it's evidence-based. So if I tell you a story, I have to also tell you the basis behind the story. Why do we believe the story? Why do we believe what we believe, not just what we believe? So I'll tell you a little bit about this evidence, and that really has to do with using telescopes as time machines to test theoretical predictions. Okay, so I'll start with our place in the cosmos, and if I could have the lights down a little bit in the front of the room if possible, because many of my slides have a dark background. I don't know if that's easy to do. If not, it's things are pretty visible on this screen anyway. I just realized that many of my, the night sky is dark, so when I take pictures of the night sky, the background is dark. It's not my fault. It really is that way. But Jeff, this is already helping a lot. Yeah, this is good. This is even better. Yeah, thank you. So when I think of our place in the cosmos, I think of my favorite people up there. You might think of your favorite people up there. I'm going to put up an example of who I think of when I think of our place in the cosmos. On the right is my daughter. She was 7 years old at that time, and on the left is my newly adopted son at that time. Okay, he hadn't been groomed in a while, so I apologize for his appearance there. But what is common to those two entities, this form of canine life and human life, is our protein molecules. So my biochemist friends tell me that protein molecules are the basic building blocks of life. Now, if I were being absolutely precise with my language, I should say protein molecules are the basic building blocks of life as we know it. Now, we know of many forms of life here on Earth, from the simplest viruses that are made of RNA to the most complex mammals. DNA and RNA are examples of protein molecules, enzymes, hormones. These are all neurotransmitters. These are all important aspects of life. And it's fair to say protein molecules are the basic building blocks of life as we know it. Protein molecules are very complex, as this picture shows. But if we were to extend our definition of life a little bit, another way to write that phrase would be to say complex molecules are almost certainly the basic building blocks of any kind of interesting life. So if there's life outside the solar system, and there might be, we haven't discovered it, we can only speculate about it at this point. But if there's life beyond the solar system, the kinds of life we'd be most interested in better be rich, better be diverse, like the kinds of life we see here on Earth. Those are the kinds we'd be interested in. And to have any kind of rich and diverse life, you can bet that would have to have at its basis some kind of complex molecule, because complex molecules have lots of chemical bonds. They're capable of they have many degrees of freedom. They're capable of taking on many forms. Those are the kinds of life forms that we'd be interested in. Now, so to form protein molecules or to form complex molecules of any kind, you need atoms with lots of electrons and protons in them. You need things that are not right at the beginning of the periodic table, but somewhat into the periodic table. In the case of protein molecules, those atoms, I'm highlighting carbon, nitrogen, and oxygen. I'm leaving out hydrogen deliberately. Hydrogen is actually formed in copious quantities early in the universe's history. Electrons and protons are initially moving around too rapidly for them to be bound by each other's electrostatic forces. Because the universe is very hot in its early phases. Hot means high temperature means rapid motion. When electrons and protons have too high an energy, they can't bind stably because their collisions are too energetic for them to remain bound. So when the universe cools down to a certain point, about 300,000 years after the Big Bang, the first hydrogen atoms form. And hydrogen protons and electrons mate for life. They stay together for 14 billion years. Now, it's a little more difficult to produce more complex elements like carbon, nitrogen, oxygen. Actually, hydrogen, helium, traces of lithium and beryllium form early in the universe's history, just through this natural collisions of particles. But carbon, nitrogen, oxygen don't form that easily. They are actually cooked inside stars. They're cooked, when I say cooked, I mean through nuclear fusion reactions, they're produced inside stars. So you might look at this and say, okay, all's well. We know where the carbon, nitrogen, oxygen came from because we live around such a star. We live around a star that's undergoing fusion reactions in its core. That's what you see on the right there. It turns out the sun's atmosphere contains carbon, nitrogen, oxygen. You know very well that the Earth certainly contains C, N, and O. If you've been to a barbecue recently, or if you're wearing a diamond ring, or if you're breathing, which you certainly are, you're taking in nitrogen and oxygen. So these elements are present in abundance on the Earth, in the oceans, on the Earth's crust. These elements are present in abundance. But there's a little bit of a mystery here. The sun, even though it contains carbon, nitrogen, and oxygen, actually has no business to contain them, because the sun has not yet produced these elements through nuclear fusion reactions. The sun is merely converting hydrogen to helium in its core. That's what gives the sun, that's what gives helium its name. Helium comes from the Greek word for helios. The sun is merely converting hydrogen to helium. Near the end of its life, about 5 billion years from now, the sun is going to cook helium into lithium, beryllium, boron. It'll get up to carbon, nitrogen, oxygen, and then die. Die in the sense it'll stop nuclear fusion reactions. So about 5 billion years from now, the sun will have some legitimate claim to some carbon, nitrogen, oxygen, because it would have cooked it within its interior. So what business does it have containing, having some of this element today? Well, its business is it is a descendant of other stars. And what I mean by that is there are other stars. This is a picture of a star field. There are other stars that lived and died before the sun came into being. And what I mean by died is these stars rapidly cooked these elements. They went through nuclear fusion reactions. They cooked all the elements up to iron, in fact, within their interiors through nuclear fusion reactions. Turns out iron is the most stable of the elements in terms of binding energy per nucleon. So fusion is favorable energetically as long as you go up to iron. Beyond that, you don't produce elements through fusion. You actually produce them in stellar explosions through neutron bombardment in supernova explosions. But the point is, the sun is not a first-generation star. The sun was born well after some of its ancestors rapidly cooked these elements in their interiors, carbon, nitrogen, oxygen, and indeed many other elements. And these ancestral stars, they're ancestors in the same way we have ancestors. These stars died before the sun was born. They were very efficient cooks. They cook all these elements within their interior, but they're also very generous cooks. They die in a spectacular way. These stars explode when they die. And what you're seeing here is a real picture of an exploded star as it looks 1,000 years after the explosion. This is about a 1,000-year-old explosion that you see over there. So the stuff that was once inside the star, was once cooked inside the star, gets generously dispersed into surrounding space. So the sun was born out of the dust, the stardust, the exploded ashes of many, many, many stars. So, in the words of Crosby, Stills, Nash and Young, we are stardust. And for the young ones among you, you don't know who Crosby, Stills, Nash and Young are. They are not a law firm. They are a rock group. And they must have known some astronomy, because they knew exactly what they were talking about when they said we are stardust. So indeed, if you look around you, your neighbor, the chair you're sitting on, the stuff that makes up this beautiful building, all of this was once cooked inside a star. Not the sun, but some other star that enriched the cloud of gas and dust from which the sun and earth and the other planets formed. So that is actually a remarkable thing, to think that our origins are spatially quite large. That is, the elements that make up our bodies come from a large region within a collection of stars. Now, a collection of stars is what we had to be part of, and a collection of stars is what we call a galaxy. Because if we weren't part of a collection of stars, if the sun were alone, if the nebula from which the sun formed were alone with no other stars around it, there's a pretty good bet that we would be made of hydrogen and helium today, not any of these other elements. And believe me, a speaker who's made of only hydrogen and helium is far less interesting than I hope to be. Okay, and indeed, audience made of hydrogen and helium is far less interesting than you are. So this particular picture is a picture of a galaxy, but some of you have already guessed that this is not a picture of the Milky Way galaxy, because we live inside the Milky Way galaxy. We can't take pictures like this of the Milky Way galaxy. What we do instead is we take pictures of our siblings. This is our sister galaxy. She's our older sister, well, at least a bigger sister. I don't know about older. But this is the Andromeda galaxy. This is my favorite galaxy in the whole world, as Jeff mentioned, and I'll talk about it in some more detail. Now, it's worth pausing here for a little bit to reflect on what we're doing here. We live in a world without mirrors. We can't see ourselves. We can't see our Milky Way galaxy. Imagine if you lived Imagine you kids living in a world without mirrors. It will take you much less time in the morning to get ready and go to school. That would be a benefit, but the downside is you wouldn't know what you look like. You would have no idea. You'd have to look at your siblings, you'd have to look at your neighbors to figure out what you look like from the outside. That's what we do here. Another analogy might be living in a house that you can never leave. You wouldn't know what buildings look like till you looked out your window and looked at your neighbor's buildings, and that's what we're doing here. This is our neighbor, the Andromeda Galaxy. To give you a sense of scale, light would take 100,000 years to get across this rectangle. 100,000 years. Light takes 1 second to get to the moon, 8 minutes to get to the sun, 4 hours to get to Pluto, 4 years to get to the nearest star, but we're talking about 100,000 years to get across this picture. Now, we live in a very average part of the Milky Way galaxy. In fact, astronomy is a very humbling subject because it tells you over and over and over again that you're completely mediocre. You know, our planet is completely mediocre, our star is completely mediocre, our galaxy is mediocre, and people speculate our universe may even be mediocre because people talk about multiverses, not uni, but multiverses. Ours may be one of many. So mediocrity is the theme of astronomy, but it's a good kind of mediocrity in this case. Okay? So we live in an average part of the galaxy. We don't live on Castro Street in downtown Mountain View where there's lots of people, lots of stars close together. We don't live often in the hills of Los Altos. We live in somewhere near the Google campus, perhaps. You know, just a pretty representative part of town. We're about 25,000 light years from the center of the Milky Way galaxy. Now, one of the things our group has discovered, our research group has discovered over the years, is the Andromeda Galaxy is 5 times bigger than this picture would suggest. You know, when we started our work, conventional wisdom was the Andromeda Galaxy went out about as far as you see in this picture. But we've been studying stars far away from this, from the center of this picture, literally 5 times further out than this picture shows, and we've been continuing to find stars that are plausibly associated with the Andromeda Galaxy in the sense they're the right kind of stars, they have the right chemical mix, they have the right velocities, they're moving with the rest of the Andromeda Galaxy, and so on. Okay, so let me talk a little bit about that. I love this picture. This is a Robert Gendler photograph of Andromeda, and I was talking about how it's eating its children. Well, here is one of its children, M32. Those are snacks only, those two. There's breakfast and lunch up there. Lunch is at noon, at 12 o'clock, right above it. And if you look closely, you'll see there's a bridge of stars that's been stretched out from that galaxy that's immediately above Andromeda. The process is very simple. If I were the Andromeda Galaxy and you guys were a satellite or vice versa, what happens is gravity is an inverse square law force. Gravity pulls hardest on something that's closest to you. So I would pull very hard on the front row. I would pull less hard on the back row. And the people sitting in between would feel a force that's somewhat intermediate between these two extremes. What that would do is it would stretch out this galaxy by virtue of this differential gravitational force. That's what Andromeda is doing to that galaxy up there. It really is this effect is called tidal effects. This is exactly what we experience here on Earth. When the moon pulls on the near side of the Earth, it pulls harder than the far side. So the Earth tries to stretch out into a cigar shape. The Earth is made of rock, so it can't do that. But the oceans, the water on the Earth that can respond, stretches out into a cigar shape. So we have high tides at two ends, and we have low tides everywhere else. Okay, so tidal forces are very common in nature. So I studied the Andromeda Galaxy, and one of the benefits is not only is it our neighbor, it's close enough that we can see individuals within our neighbor's house. We can see individual stars within Andromeda, and I'll show you some examples of that in just a minute. To see individual stars in Andromeda, you need powerful telescopes. So we use the Hubble Space Telescope a lot, but we also use the Keck telescopes that Jeff and I visited in August. Here's a picture of the Keck telescopes. There you go. There are 2 Keck telescopes. They are the world's biggest optical telescopes. If you were to put the mirror of the Keck telescope in this room, it would occupy about the space occupied by the seats here. It's about 10 meters across, 10 big steps across in diameter. So they're very, very expensive, and of course we've done the right thing and we put them right on top of a volcano in Mauna Kea. And we're keeping our fingers crossed that the volcano is dormant for a long time or hopefully even extinct. So I use one of these two telescopes a lot to study the Andromeda Galaxy, and I'm going to show you some more details of these telescopes. It's a little difficult to get a sense of the scale of these telescopes just looking at these pictures, because the top of Mauna Kea looks like it has a lunar landscape. There are no trees, there are no rocks. I mean, or there are rocks, but there's no sense of how big those rocks are. So just to give you a sense of scale, somebody has conveniently parked an SUV right there. That's an SUV. That's a bigger than average car. That building, my guess is it's about 15 stories high. That's how, but it just looks like a tiny little, looks like a little football helmet that somebody's placed on the field, but it's really large. Let's look inside it, and I'll show you a couple of views. In this particular view, you see the telescope, which is sort of pointed horizontally in this view. The telescope, the piece of glass, is actually made up of 36 segments. The segments are hexagonal in shape. You can probably make out these hexagonal shape. Each hexagonal element is about 6 feet tall, 1.8 meters in diameter, the size of a human being, good size human being. So again, nothing to reference anything by, so it's very difficult to get that sense. In this picture, you do get a sense of scale. These are not plastic models. These are real human beings. They are standing next to the silver cylinder, which is the camera portion of the telescope. The Demos spectrograph that I use a lot was built in Santa Cruz. I've walked inside the spectrograph, or you can walk inside this camera, because as telescopes scale up, so have the instruments got to scale up proportionately. In the same way that we now have tiny little cameras that are embedded within cell phones. Technology is also obviously pushed in this direction in the size of making things bigger. So with this spectrograph, you can take spectra of individual stars in the Andromeda Galaxy. That's what this is. This is a raw spectrogram. It's a very unusual view of the Andromeda Galaxy. It's one that spectroscopists are used to, but this is the Keck telescopes are used for this, one of the two Keck telescopes. DEIMOS is the name of a spectrograph. It stands for Deep Extragalactic Imaging Multi-Object Spectrograph. It's probably the most powerful spectrograph in the world. It was built at Santa Cruz by Sandy Faber. And we can get spectra of something like 250 to 300 stars at once. So I'm going to zoom in a couple of times. And you zoom in, you can now see that there are vertical bands running through this picture. There's about 250 vertical bands across the whole thing, but you see a subset of them here. So the first thing you learn is textbooks are wrong. Textbooks always show spectra running horizontally. Well, in the DEIMOS spectrograph, they run vertically. This is a real spectrograph in my mind. Spectra now run vertically. So each band is a spectrum taken through a cut in a piece of metal called a slit. So you cut a slit at the right location of a piece of metal. So when you point your telescope right, there's a star shining through it. In fact, if you look closely, every one of these bands has a streak going vertically through it. That's the light of an individual star in the Andromeda Galaxy. I'm not kidding you, that's what that is. What is even more prominent than those vertical streaks are these horizontal lines here. They look like barcodes. In fact, you can see this code over here. You see the code repeated here. You see it shifted a little bit and repeated there. You see it shifted even further up there. In this one, it's shifted way up. In these two, it's shifted way up there. In this one, it may be shifted off the screen. This barcode, this repeating barcode, is a signature of the Earth's atmosphere. So the Earth's atmosphere, even at the darkest site, Mauna Kea is a very dark site, but if you go to even to a very dark site, the Earth's atmosphere actually glows. There's oxygen and OH in the Earth's atmosphere. It glows. It puts out things called emission lines, light of very specific wavelengths or frequencies. Those create this pattern. Since all of these slits are looking at the Earth's atmosphere, even if the stars beyond the atmosphere, it can't help but get light from the atmosphere. Since all of them are looking at the same atmosphere, they all have exactly the same barcode. The shift from one slit to another has to do with the physical placement of the slit within the focal plane. Because different stars, the stars are not aligned in a convenient line like that, they're in different parts of our field of view. So because the slits are positioned according to the locations of stars, the barcode shifts up or down accordingly. So this is in fact, the Earth's glow is in fact the reason why you cut a slit to look at a star. A star looks like a blob. Why not cut a circle in a piece of metal? The difficulty with cutting a circle is the light that would come in through the circle would be the light of the star and the light from the Earth's atmosphere, and you would have no way of telling those two apart. So by cutting a slit, you can look on the star and off the star, and you can use the part that's off the star to subtract off the effect of the Earth's atmosphere. This is a process called sky subtraction. You subtract the sky, but I don't mean the sky, the blue sky above you. You never subtract that, but you subtract the glow of the night sky in this way, the signature of the night sky. So with the help of spectra like these, we can measure how fast each star is moving. We can measure its velocity. We can measure what chemical composition it has. That's important, vis-a-vis the discussion we've just had earlier about chemical evolution. And in fact, one of the lines I study a set of 3 absorption lines in stars quite a lot, and they are produced by calcium ions in the atmospheres of these stars. So it's quite remarkable to me that you can take a galaxy that's, Andromeda is about 2.3 million light years away. You can take individual stars in that galaxy, and you can figure out, just by understanding the properties of light, you can figure out what its chemical composition is, how fast it's moving, and how fast it's moving actually tells you about what gravitational field these stars are experiencing, which in turn tells you how much dark matter is contained within the Andromeda galaxy. So this is remote sensing at its best. Astronomy is mostly about remote sensing because you're only getting light from a distance. That's all you get. All right. So I've talked about the Andromeda galaxy a fair bit, and it's a good sibling of the Milky Way galaxy, but galaxies come in many shapes and sizes, some strange and some not. This one has this lovely little twist going through this hula hoop that's around this central ball of stars. This is a view of another galaxy, probably similar to the last one, but happens to be viewed from pole on. So you're looking at it from top down or bottom up, as you like. And these colors actually mean something. So these pictures are taken with real telescopes. These colors mean something. When you see yellowish white at the center, you're seeing old stars, sun-like stars. When you see bluish white, as you do in the ring, you're seeing young stars, massive stars typically. Those are the ones that are capable of rapid nuclear fusion reactions. Those are the ones that produce many of the elements that we see in the sun and earth today. You see really bad-looking galaxies. This one's having a terrible day. And these blemishes that you see, these so-called blemishes that you see, are extremely important. And I'll talk about those. These dark clouds that you see against the face of the galaxy are actually birthplaces of new stars. So they're dark, not because there are no stars there. They're dark because they're blocking the light of stars in the galaxy in the same way that a cloud on a cloudy day can block the light of the sun. That's what these clouds are doing. These are giant clouds. They're much bigger than clouds in our atmosphere. Here are 2 galaxies that are going through some kind of collision. I just want to give you a flavor of different kinds of galaxies. Here's another one where you can see a collection of these clouds of gas and dust. This is actually the near edge of the Frisbee. The Frisbee is oriented like this, and these clouds of gas and dust are blocking. You can see them in silhouette. Here's another one that is, again, seen at a jaunty angle. You were worried about circles looking oval. Well, this is what I meant by most of my pictures are already oval. Just to give you a quick, just a very quick primer on why galaxies look the way they do. So this is a spiral galaxy. You can see why it's called a spiral galaxy right away. It has these spiral arms. Galaxies spin in a very unusual way. When you think of a Frisbee spinning, every part of the Frisbee completes a circle in the same amount of time. That's not how galaxies spin. Galaxies, by contrast, most stars move at the same speed. They move at the same speed. If you're running in a circular track and you're all moving at the same speed, the person in the inside track has an advantage. So stars in this part of the galaxy have an advantage. They can complete many circles in the time that a star in the outer part completes one circle. So this is what gives galaxies their sort of twisted up appearance like this. And the best analogy I can think of is if you take dark coffee and spin your cup of dark coffee, the coffee that's against the walls of the mug, because of friction, that coffee is not spinning very rapidly. The part in the center is spinning rapidly. Coffee exhibits differential rotation like galaxies. If you put a little bit of cream into that, it gets an appearance like this. The cream in the case of galaxies is the birth of new stars. When new stars are born, the bright patch gets sheared out into the spiral pattern by the differential rotation of galaxies. There's actually a very well-developed theory, spiral density wave theory, that explains the appearance of spiral galaxies. Okay, here's a spiral galaxy, that same one that you saw in the last picture. A different one from the previous picture, naturally. We can't take different perspective images of the same galaxy. That's one of the banes of astronomy. We're stuck with the perspective we have, for the foreseeable future. And here's another one. Here's another galaxy that we happen to see perfectly along its edge. People have taken this galaxy and they've said this one is just like the Milky Way. In fact, our view of this galaxy, if you look at this rectangle, our view of this galaxy, we're not at the center, we're not right at the edge, we're somewhere here. So our view of the galaxy is sort of like the view of this, our view of this galaxy. So you don't need to take my word for it. Here's a picture of the Milky Way taken from the southern hemisphere. This is a telescope in Chile, fisheye lens, looking at a large patch of the sky. The horizon looks curved like this because of the distortion in the camera, but you can see the Milky Way beautifully going across the sky. It's a Milky Way, it's a band of light, and if I go back and forth between this picture and this one, you can see the similarity. Now, just a pause here to talk about the word galaxy. The word galaxy actually comes from the Greeks. Astronomy is a very, very old science. Astronomy has been around as long as civilizations have been around. This is one of the beautiful things about astronomy. It's also a very new science because it's technology driven, and every time there's new telescopes, new detectors, we make advances. So the ancient Greeks, well, maybe not all of the ancient Greeks, but the ancient geeks among the ancient Greeks decided that this looked like a band of milk across the sky, and the word galacto and the word lactose are all rooted in the word for milk. So what we've done is we've taken the appearance of our own galaxy and we've called every galaxy the same thing. We call every galaxy a band of milk. So that's what the word galaxy means. So it's pictures like this that give us confidence that we live in a spiral galaxy, and we live among these clouds of gas and dust that you see cutting a dark band across the Milky Way. What I'm going to do in the next few slides is focus on these particular clouds of gas and dust. I said they were important because they're birthplaces. Well, here's a detailed view of one of these. Astronomers have lovely romantic names for these things. This one is called NGC 6357. This is a picture taken with the Hubble telescope, and the colors are something that's worth paying attention to because this is what the eye would see if it was sensitive enough. So the red hue is actually the glow of hydrogen alpha. This is electrons cascading down from level 3 in the hydrogen atom to level 2. Produces this intense red color. You see a piece of a cloud of gas and dust. You see a young star that's been born. It has carved out a little cavity. It's created a little cave for itself. It's peering out. It's in time, it'll actually blow away the material that it was formed from. Stars commit fratricide. Once they're born, they prevent other stars from being born around them. You can see that they're also born in groups. There's a litter of stars, just like puppies. They're born in groups. Okay, so you see a group of stars in the upper part of this picture. Those stars are freshly formed stars from this cloud, but they've eaten away at the cloud they were in their immediate vicinity. The intense radiation actually exerts a pressure, ionizes and blows away the cloud around it. Let's look at this process in a bit more detail. This is the Orion constellation. You might recognize the shoulders, the belt, the sword of Orion. Turns out the sword of Orion, the bright spot there, is not a single star, but it's a nebula. In fact, this is a wonderful picture taken with the Hubble Space Telescope of the Orion Nebula. And we'll zoom in a few times. Hubble has amazing detail. And with pictures like this, Hubble also has this great benefit that when you take pictures, they come with circles marking interesting things. No, just kidding. That doesn't happen. Someone's gone in there and marked these circles to mark interesting objects here. And what are these interesting objects? Let's zoom in a little more. So the interesting objects here, these 4 objects are young stars that are in the process of being born. So every one of these 4 is a star. You can see this star quite clearly, but it's got a plume of gas and dust around it. This one, the star is actually hidden from view. You see a sort of silhouette of a dust cloud. And in the other 2, these stars are trying to make their presence felt. They're trying to break free from the little piece of cloud they formed from. These 4, on the other hand, have more or less broken free. You can now see through to the stars, but they have a little band of, a dark band around them. They're actually surrounded by a disk of material, these stars. Now, these are real stars. These are They're called protostars. They're on their way to becoming real stars. They haven't quite started their fusion reactions yet. Here's one that particularly advantageous view. This is one that's seen along its edge, and you can see the star peeking out from the top, but you can see this edge-on view of a dust disk, 17 times the size of Pluto's orbit, so only slightly bigger than our solar system. And these are called proplids. They're in Orion. Pro stands for proto, so they're protostars. Well, they're protoplanetary disks. Protoplanetary disks. These are disks of material that will give rise to planets. So they're protoplanetary disks. And so far, I've been showing you pictures taken with telescopes. I'm going to give you an artist's view of a simulation of what these dust disks might look like if you had enough detail. If we had enough detail. We don't have this kind of detail yet. But this is a little movie showing how these debris disks of dust and rocks might evolve. You can see a channel opening up here, probably because there's a planet forming there, sweeping things accreting material. So planets grow by sweeping up this dust and gas. And over time, the giant planets clear out everything in this dust disk, and you're just left with these coagulated elements, which are the planets. Okay, so this is an artist's view, I say, but based on some pretty detailed physics calculations. Formation of a system of planets. All right. So just to wrap up this cosmic evolution idea, this cosmic chemical evolution idea, chemical recycling idea. Here's a picture of a galaxy with a spot in it. Now, this picture of a galaxy comes from a really boring project. There's a group in Berkeley that does an extremely boring project. They go to the telescope every night and they take pictures of the same galaxies, night after night after night. They have a list of galaxies and they just take pictures of the same darn things every night. But once in a while, they get lucky and they see a spot in the galaxy where there wasn't one the night before, or there wasn't one the week before. That's an example of one such thing. That spot that you see marked supernova wasn't there the previous night, or 2 nights back, whenever the previous picture was taken. That's an example of a star that's in the process of exploding, and it's probably a young, massive star that's exploding. You can see it's relatively close to this disk of dust and gas. At its brightest, a supernova, a stellar explosion, can outshine the rest of the galaxy. Depending on the size of the galaxy, a single star can outshine the rest of the galaxy. This is not too far from it. In fact, it's hard to see. The star's light is saturated in that spot there, but there's a lot of light in that spot. If you give it 1,000 years, it expands into the ejector, the stuff ejected from the explosion, spreads out, and enriches surrounding clouds of gas and dust, interstellar gas and dust, out of which young stars are formed, new stars are formed, which then go through their own fusion reactions. So this is the cosmic chemical cycling we've been talking about. Now, Sandy found this amazing picture taken by an astrophotographer. I wanted to show this. And Sandy and I saw some real poetry in this picture. Wally Pacholka may have seen the same poetry in the picture when he took it. This is an astrophotographer's photograph of a cave in the southwestern United States. Okay, this is looking out of a cave, I believe in New Mexico. You're looking out. You see a bunch of rocks here. You see an arrangement of these rocks suggesting that this was a family's home, perhaps even a community's home in ancient times. But if you think about these rocks are made of iron, silicon, magnesium, oxygen. It's made up of a bunch of elements in the periodic table. These elements in the periodic table wouldn't exist if it hadn't been for the fact that our planet and our solar system and our sun are part of a family that's part of a grander home, and you're seeing that grander home through the opening of this cave. So this immediate home belonging to some family or community is embedded within a much larger home, and that's what gave these rocks their existence. So there's a beautiful symmetry to this picture. All right, so we've been talking about galaxies and why galaxies are important, and I hope I've convinced you galaxies are important, but I haven't quite told you where galaxies come from, and so I want to spend the next few minutes talking about that and taking you sort of further back in time, in fact taking you back to some of the earliest imaginable moments in the universe's history. So to do this, I want to give you a sense of what our environment looks like. So I'm going to play this movie, And I'll talk while this movie is being played. This is a movie where you can see the Orion constellation, but very quickly you'll see the Orion constellation break up into sort of funny shapes because this movie has realistic distances attached to everything. So this is really a series of astronomical pictures that have been stitched together in a clever way by Brent Tully, one of the astronomers who studies the structure of the Milky Way and things in it. And we're flying at an unrealistic speed here, just to be sure. Kids don't expect to be actually able to take this journey. This is a virtual tour of most of the solar system, most of the galactic system, and in fact we'll go beyond the galaxy in a bit. And this is a very unusual journey. This cosmic pilot has this real sense of bravado, takes us to the most dangerous parts of our galaxy. So we just went through an exploded star. But what is remarkable about this picture is it is based on actual astronomical images. I like to think of it as a documentary because it's a series of real images that have just been stitched together in a meaningful way. There is a small bit here, though, where it goes from being a documentary to a docudrama in Hollywood terms. So Brent goes Hollywood for just a little bit, and it's not by choice. He has to go Hollywood in this segment because we've never taken pictures like this of the Milky Way from the outside. So in this case, there's an actor playing the role of the Milky Way. There's a different galaxy that's being used to portray the Milky Way, just for this segment. And then we go back to documentary mode because these are two real pictures of satellites of the Milky Way, the large and small Magellanic Clouds. You'll see the Andromeda galaxy coming in from the upper right with its companions. There she is, okay. Andromeda with one of its companions, and here's another one of Andromeda's companions. And you'll see as we fly through that galaxy, that's M33 over here, this galaxy we're about to fly through. That has exploded stars within it. We're going to fly through one of those. And what you see very quickly, each of these galaxies is tens to hundreds of thousands of light years across. They look like tiny blobs, but each of these things is a galaxy. It's, some the size of the Milky Way, some bigger, some smaller. And in fact, there's this lovely concentration of galaxies over here. This is called the Virgo cluster. It's in the constellation of Virgo. There's a lovely cluster of galaxies in Virgo that it's our nearest big concentration. But it gives you a sense that we're not alone. We're not alone as planets in the solar system. We're not alone as stars in the Milky Way. The Sun is one of 100 billion stars in the Milky Way. And indeed, the Milky Way galaxy isn't alone. It's part of a family. We're part of a group of galaxies called the Local Group, but we're not too far away from an even bigger collection of galaxies called the Virgo cluster. In fact, the biggest galaxy in the Virgo cluster, M87, this one, has a supermassive black hole at its center. We now know that every galaxy worth its salt has a black hole at its center. So in true to her form, this pilot is going to crash land us right at the center of this black hole, at the center of M87. Okay, so the idea behind this movie is to give you a sense of where we live, our neighborhood, our galactic neighborhood. And you might have noticed that galaxies are not distributed uniformly. They're distributed in clusters and clumps. And one of the great advances of the last decade has been high-powered computer simulations. In fact, the first of these was published in 2000. It was called the Millennium Simulation. We made a lot of progress since then. And I'm going to show you the results of the Millennium Simulation, where you start out with a universe that's more or less smooth, but over time, gravity takes over and takes tiny little ripples that you saw early on, polarizes them, makes their amplitude greater. If it's a tiny trough, if it was slightly less dense than average, then that region completely empties out, and you see the formation over time. You see time counting up in the upper right. Gigayears is the unit, billions of years. So we're at a quarter or a third of a billion years there. But it's going to go all the way to 14 billion years. But given enough time, gravity can act, and it can turn even tiny ripples in the fabric of the cosmos into these amazing structures. This particular structure, you're all familiar with the World Wide Web. This particular structure is called the cosmic web, and it's somewhat larger than the World Wide Web. This is, just to give you a sense, a Milky Way galaxy might be something like that blob moving up there. So the Milky Way galaxy is really very, very ordinary in this. Yes, please.
Is the rotation from the observer, or is there initial?
This video is a bit confusing because our perspective is changing. This is not real rotation, it's merely perspective that's changing. So we're both moving and it's collapsing under its gravity? It's a good question. We don't expect nearly this much rotation. We expect some rotation in systems, and you'll occasionally see that. But most of this swirling motion that you see here is real, because that's going on. But our perspective is changing. We're also zooming in somewhat, because you can see this bar was much smaller before. A kiloparsec, by the way, is about 3,000 light years. So this is 500 kiloparsecs. So much bigger scale than individual galaxies. I should emphasize also, this picture is a map of how the dark matter in the universe would evolve. Not stars, but how dark matter would evolve. So it's a detailed calculation of the gravity that every particle feels relative to every other particle. And I just want to explain this very, very simply. If you have a sea of particles, if it's a perfectly uniform sea of particles, a particle in that uniform sea would feel an equal pull in all directions. So there'd be no net motion. There'd just be the expansion of the universe. There'd be no net motion relative to other particles. The patterns would stay fixed. If, on the other hand, you live right next to a slightly dense region, you've got particles pulling you in all possible directions, but you've got a slightly extra number of particles, slightly higher number of particles pulling you in one possible direction, where that ripple is, where the overdensity is. So you tend to migrate towards that. So something that's slightly richer than average gets even richer over time. The rich get richer, the poor get poorer, thanks to gravity. Gravity is a great polarizing agent in that sense. Okay, so this was a dark matter simulation. You see it stopped at about 13 point some billion years. That's how old we believe our universe to be. That's how much time we think has elapsed since the Big Bang. This next simulation is a zoom in on one of these filaments in the cosmic web. And this time, not only is dark matter's gravity being modeled properly, but dark matter isn't even being shown here. It's hidden in the simulation. Gravity is being modeled properly. But what is being shown is the response of gas and dust to the gravity of dark matter. And now you'll see things forming that look more like galaxies. They don't look like blobs. The dark matter is much more blobby. Gas and dust tends to form along these filaments, tends to congeal along these filaments. You can see these two galaxies about to collide. And while this cosmic wreck is going on, you'll see that other galaxies, like these two galaxies, are in the process of colliding. You see some rubberneckers going by on the cosmic freeway. But these two galaxies are colliding. And you might look at this and say, these don't really look like galaxies. They look like a complete mess. In fact, galaxies, we think, look like complete messes early on. Over time, as the cannibalism occurs. The cannibalism is actually a very strange kind of cannibalism. It's more like a corporate merger. When galaxies smash into each other, stars don't smash into each other. They merely switch loyalties. When you have two galaxies, you've got two centers of loyalty. You've got a bunch of stars going around one center. You've got another set of stars going around another center. When they collide, they're going around a common center. And now you can begin to see that this entity that looked like a complete mess before is starting to look like some of the images you've seen of spiral galaxies. So these simulations, these sort of computer simulations that show the cosmic web, and now we're changing our perspective. Nothing is happening to the simulation. We are just moving from the lower part to the upper part of the simulation. You can see there's a swarm of stars in the center, there's spiral arms. I think this represents one of the triumphs of modern day computing as it pertains to astronomy and cosmology. You produce realistic looking galaxies. This particular one was done in Japan. All right, so far, sort of going on with this story, we think galaxies form because of gravity, but gravity needs something to latch onto. You need these ripples to be present in the fabric of the universe. So you have to ask the natural question, why didn't the universe start out perfectly smooth? Why were there these little bumps and wiggles in the universe? And the answer to that, there are two words to answer that, and that's quantum mechanics. Quantum mechanics is the reason why the universe didn't start out perfectly smooth. Now, instead of trying to explain quantum mechanics, I'm going to put up a little cartoon here. Where there are two quantum physicists. One says to the other, "Oh, Alice, you're the one for me." And Alice, being a really smart quantum physicist, says to Bob, "In a quantum world, how can we be sure? There's a lot of uncertainty that quantum mechanics teaches us about." Okay, so I can't resist this. Professor Heisenberg is the person who is responsible for coming up with the uncertainty principle. There was lot of opposition to quantum mechanics when it was first proposed. Einstein was one of the great opponents of quantum mechanics. He said, how can something as beautiful as the universe be governed by chance? Einstein had a famous quote. He said, God does not play dice. That was his famous objection to quantum mechanics. Einstein was wrong, as it turns out, because he came around later to try to incorporate quantum mechanics into his theories. But Einstein was scolded appropriately in those times by Niels Bohr. Niels Bohr, someone who was a quantum physicist, studied the structure of atoms. When Einstein said, God does not play dice, Niels Bohr said to Einstein, how dare you tell God what to do? This was a very, very deep debate going on about 100 years ago. And quantum mechanics, it's fair to say, even today, is not very well understood. The joke goes about Heisenberg. Momentum and position can't be predicted absolutely precisely. So if you can measure x, the position, if there's a certain uncertainty in that delta x, momentum p, delta p, the product of those two is finite. It can't be zero. So if you know your position, you don't know your momentum very well. If you know your momentum precisely, you don't know your position very well. So Heisenberg's driving along the Autobahn one day. He's speeding as usual. The cop pulls him over. The German cop does the same thing that cops all over the world do. They ask you this question, do you know how fast you were going? And Heisenberg quips, no, but I know exactly where I was, because the uncertainty, momentum, and position. If you don't know your speed, you know your position very well. Okay. Jokes aside, another way of stating the uncertainty principle is to say that delta E times delta T, delta energy times delta time, is a constant. So, dimensionally, in terms of units, if you take the units of position and momentum and multiply them together, they're the same as the units of energy and time multiplied together. So if you know exactly which instant you're talking about in the universe's history, then you can't predict the energy of that parcel of the universe with arbitrary precision. So quantum mechanics imposes on us these fluctuations just because of the uncertainty principle. So delta E, delta T being the product of those two being constant means in early times, when you have to know the time precisely, there were fluctuations at the level of 1 part in 100,000. So at the level of 10 to the minus 5, there were fluctuations. Now, normally you think, okay, these are fluctuations in the quantum domain, microscopic, they don't really affect us, but it turns out they do affect us. And the person who convinced us that quantum fluctuations affect us is Schrödinger. Schrödinger came up with this experiment called the Schrödinger cat experiment, and in which he said, let's devise an experiment, a Gedanken experiment, a thought experiment. He didn't actually carry this out. No animals were harmed in the making of this experiment, okay, as they say in the movies. So you start out with a radioactive particle or a group of radioactive particles, and you put them in a box. You close the box. You come back after an hour. There's a 50% chance that the radioactive particle would have decayed to produce an alpha particle. That's a helium nucleus, 2 protons and 2 neutrons. The alpha particle has a certain probability of existing an hour after you've started the experiment. Certain probability, so let's say 50% probability it exists, 50% probability this hasn't decayed, in which case the alpha particle doesn't exist. If the alpha particle was created, then there's a Geiger counter. Normal Geiger counters beep. So since this is a Gedanken experiment, Schrödinger says, let's set up our Geiger counter so that it doesn't beep, but instead has a hammer fall, and you get the sound of breaking glass as that hammer falls on a bottle, on a glass bottle that contains poison. That stuff is lethal to cats. So that's why there are 2 states of this cat. The cat can either come out like this, all happy, or like that, where it is unhappy and you're unhappy if you're its owner. So those are the 2 possible states of the cat in the Schrödinger cat experiment. 50% chance it comes out in the upper state, 50% chance it comes out in the lower state. Now, Schrödinger didn't carry out this experiment. But there's an uncertainty in this experiment. If you set up 1,000 of these boxes, you can't predict beforehand which of these cats is going to end up in the upper state, which one's going to end up in the lower state. That's the uncertainty. You cannot predict the fate of an individual entity in this scenario. Schrödinger didn't carry out this experiment, but the universe went ahead and did it. The universe went ahead and did its version of the Schrödinger cat experiment. This is a timeline in the universe where you have the Big Bang on the left, the present day on the right, 14 billion years after the Big Bang. You've got, shortly after the Big Bang, there were quantum fluctuations. And just like the Geiger counter takes these tiny microscopic phenomena, moves them into the macroscopic domain, in this case, inflation, this very rapid expansion in the universe's history, there's a very rapid phase of expansion in the universe's history. It lasts for 10 to the minus 23 seconds, and the universe expands by a factor of not by 2 or 4 or 10, it expands by a factor of 10 to the power 50 during that time. Inflation is here to stay. Even though it sounds crazy, it's here to stay. It's something that explains a lot of things in the observed universe, and it is the thing that takes these quantum fluctuations, blows them up, freezes them into the fabric of the universe. So in a real sense, if something was slightly lower than less than average, it becomes a void. If something was higher than average, it becomes a galaxy. A galaxy is a live cat in the Schrödinger cat experiment. A void between galaxies is a dead cat in the Schrödinger cat experiment, in the universe's version of the Schrödinger cat experiment. Okay, finally, 3 predictions. Galaxy collisions should be common. Galaxy collisions, unfortunately, take a long time. They take 1 billion years to unfold, and no astronomer has had that kind of time to watch them. So we have a computer simulation instead. And what we're going to do is watch what happens to these 2 galaxies as they get closer together. We're going to stop the simulation, and you'll see 2 pictures of real galaxies that are about to collide. Then we'll go back to the computer simulation, let gravity do its thing over time, and you can start to see the distortions happen in this galaxy as the near end is being pulled harder than the far end. Again, we'll stop and change our perspective, so you can see a pair of real galaxies that are going through this process. Here are 2 real galaxies that are in early phases of the collision. Now, we wait a little bit longer, you can start to see the distortion very clearly now in these 2 galaxies. They're stretching each other out. And let's stop, and here are 2 real galaxies going through this process. So galaxy collisions are very common around us. They last a long time, but the advantage is we have many of these, so we can see snapshots of different phases of a galaxy collision. Infant galaxies should look ragged. You saw in those simulations, early galaxies look terrible. They don't look like nice symmetric things. So here's a picture taken with the Hubble telescope that lets us look at infant galaxies. The way you look at infant galaxies is very simple. When you're studying infants on Earth, you just have to gather up kids, and you can see children, adults, very easy to do that. In the universe, it's just as easy. All you have to do is look around us, and you're going to see near us are things that have been around for a long time. Far away from us are things that haven't been around for a very long time. The reason is simple. Let's zoom in. I'll explain what I mean. If you look at a galaxy like this is 3 billion light years away from us. The universe is 14 billion years old. If that galaxy is 3 billion light years away, light has taken 3 billion years to travel from that galaxy to us. So the universe was 11 billion years old when light left that galaxy. The information is always backdated, and it's backdated by an amount that depends on how long that information's been transmitting, how long that light has been traveling. So here's another galaxy that's 7 billion light years away. It left the universe when the universe was middle-aged. When the universe was 7 billion years old, light has been traveling for 7 billion years. And you can see that that galaxy is not nearly as symmetric and organized as this one. And in fact, if you look 10 billion light years away at yet another galaxy, you can see that this is like a teenage galaxy. It's still troubled. It's trying to find itself. It's trying to get itself together. You can see that the different pieces of the galaxy are in the process of organizing. Now, these sorts of pictures were taken with the Hubble telescope, but there's a lovely technique that astronomers have adapted from SDI, from Strategic Defense Initiative, Star Wars. Those of you who remember Star Wars from the Reagan years. We had these satellites looking down at the Russian missile silos, and we couldn't get detailed pictures of them because the Earth has an atmosphere that's moving around, so we get distorted images. It's like looking down into a swimming pool and trying to read some writing at the bottom of the pool. You can't because the water's moving around. So if you have an adaptive system that corrects in real time for the distortion, then you can fix this. And astronomers, of course, use this technique, but they look in the other direction through the atmosphere. They look from the bottom up. And as you see these light waves come in, you'll see that when light comes in, they should come in as plain waves, but they don't, and that's why stars twinkle. So you'll see these waves coming in. They look like potato chips. They don't look flat. In fact, they don't even look like Pringles potato chips. Pringles potato chips, all of them have the same shape. Here, you see the shape is changing all the time, so that mirror dances equal and opposite to the changing shape, and that causes the star to stop twinkling. So this is a technique called adaptive optics. And it is, a simple way to remember it is, Untwinkle, untwinkle little star is a good way to remember adaptive optics. So it's an amazing technique used to take sharp pictures. Now, this is just to reinforce the idea of looking back in time. If you look close to us, you see old things. If you look a little bit further away, you see slightly less old things. And you look even further away, you see things that are halfway through. You see younger entities. And one of the amazing things about astronomy is you can see unborn entities. You can see unborn galaxies. Astronomers love doctors. They keep us alive, but they also, medicine makes astronomy look like an exact science. I don't know how this doctor decided that that was a foot, but we'll go with it. And what it's pointing to over there are the ripples that give rise to galaxies. So I want to talk about that next. The last of these predictions, I said I'll talk a little bit about these predictions of the story, is you can actually see the ripples in the cosmic ocean that give rise to galaxies. Here's a picture taken with radio telescopes of the sky all around us. So it's projected onto a globe. Oops. It's projected onto a globe. Let me see if I can play this movie here. What you're seeing is the afterglow from the Big Bang. The Big Bang was a very hot phase in the universe's history. Just like you can turn off your barbecue oven, but it takes a long time for the embers to cool. The embers of the universe are still cooling, but you can see that the afterglow from the Big Bang was not perfectly uniform. It has ripples at the level of 1 part in 100,000. These are the tiny fluctuations that gave rise to galaxies. Okay, so I hope I've convinced you that biologically and chemically our history links us to galaxies, to Milky Way and Andromeda. Galaxies grow through cannibalism. They grow from tiny seeds in the universe's fabric. So really, our true ancestors are quantum mechanics, blown up by inflation, and then gravity amplifies them over time. So you start out with these ripples in the cosmic ocean. You take a little hotspot there, and that grows into an infant galaxy where the pieces come together to form a nice symmetric galaxy in which stars undergo chemical fusion reactions, enrich the space around them through explosions. Out of this material, our planet and star were formed, complex molecules and wonderful entities like these. Okay, so that's the end of our cycle. And I thought I would spend just one slide talking about the science internship program that Jeff referred to early on. We have high school students doing research at Santa Cruz. And in fact, we have freshmen coming in, high school freshmen coming in, high school seniors. And I want to emphasize that these are real research projects they're doing. They're not just doing something where they're given a problem where the answer lies on a certain page in the book. No, these are problems for which nobody knows the answer, not the person assigning them the problem, and certainly not the student who's doing the problem. They're real research projects. That's how projects are in the real world. They don't have answers written somewhere. If they were, they wouldn't be problems anymore. And the topics in which these students are doing research include astronomy, physics, chemistry, biomedical engineering, marine biology. I think we're going to add computer science. We're going to add a few other topics this coming summer. It's been going on for 3 years. The high school students' projects are part of bigger projects that are being worked on by PhD students, postdocs, faculty, undergraduates. So they're part of a community. They get to see how science actually works, the process, not just the results. And the students have been amazingly successful in national science competitions. So it's been an extremely, extremely rewarding experience for me. My work gets amplified tenfold every summer. The productivity of my research group gets amplified every summer. And in fact, so much so that we're continuing this project during the school year in their spare time between the schoolwork duties. The students are continuing their projects. So that's where I'll stop. Thank you for your attention. That's a very good question. So the question is, how do you square inflation with the speed of light? So yes, if you're going to expand by a factor of 10 to the 50 in 10 to the minus 23 seconds, it means particles move apart from each other faster than the speed of light. This is one of these well-hidden secrets in relativity. Special relativity tells us that nothing can travel faster than the speed of light. General relativity happily allows that. allows that if the gravitational fields are strong enough, if space-time is curved, not flat in topology terms, in general relativity terms, then it does allow travel faster than the speed of light. Inflation was designed to satisfy Einstein's field equations of general relativity. So yes, it does involve travel faster than the speed of light, and yes, relativity allows it. General relativity allows it.
I think they're not really moving away from each other. The space between them is expanding. It's not the same thing as a movement. You can't look at it as a gravity wave. It's not an explosion where particles fly away from each other.
But if you take any given pair of particles, their relative speed is faster than the speed of light, and that is allowed. That is allowed in curved space-time. Sorry? In what manifold? Well, in this particular case, they're talking about a 4-dimensional space-time. They're talking about 3 dimensions of space, 1 dimension of time. So nothing exotic in this particular case. I have to take this question, please. There is such a thing as neutral matter, of course there is. Electrons and protons are negatively and positively charged respectively, but there's a particle called a neutron, for example, that has no charge at all. And you may have heard there are also particles called neutrinos. There's been a lot of flap recently about some people think neutrinos might be traveling faster than the speed of light. That hasn't been confirmed yet. There's a joke about this that's going around that says, the bartender says, we don't serve neutrinos here. A neutrino walks into a bar because, causality is reversed. Okay, yes, go ahead, please. Yes.
What I meant is like a neutral matter is it's not dark matter, nor is it any matter that we know of.
Well, if we don't know of it, I wouldn't be able to talk about it, right? I think I understand what you're asking. I think what you're the way when people talk about dark matter, why even talk about it if it's dark? Might be a question. Dark matter is known to exist. I want to emphasize that dark matter is known to exist because even though we don't see any light from it, we can sense its gravity. So the reason people talk about dark matter is because galaxies are spinning much faster than they should. Galaxies are spinning much faster than they should if the only gravity they were feeling were the gravity of all the stars in the galaxy. The speeds are way too high, by a factor of 10, way too high compared to to the gravity the stars should be feeling if stars were the only thing present in the galaxy. So that's how we know dark matter is present. It's through we can sense its presence through its gravity, even though we can't see its light. I don't know if that answers your question at all. Yes, please.
Is there any evidence that other universes exist?
That is a tremendously good question. The question is there any evidence that other universes exist? People speculate about it. They think about it. They make theories about it. I think it's unlikely that we'll ever be able to confirm whether other universes exist, because by definition, our universe is everything we can sense, everything that can send us signals. So when we're talking about another universe, it means we can't make any measurements of it. We can speculate about it, and in fact, it's nice to speculate about it, to say that our universe is ordinary. It's not a universe. It's part of a multiverse. We can speculate about it, and it's nice philosophically. But when it comes to the language of physics, of getting hard evidence, I think it's going to be very hard to prove one way or the other. Okay, let me take those two questions and I'll come back to you. Okay, let's start with you.
If there is possibly a multiverse, then like galaxies, wouldn't they collide and we would know about the multiverse?
That's a very good question. Would we know about a multiverse? By definition, if we're talking about another universe, not ours, at least as I understand it, as physics portrays it today, it would have to be a piece that we're not able to communicate with at all. We're not able to see, we're not able to get any information from. So it doesn't necessarily mean that galaxies would collide because of that. Galaxies collide anyway. Galaxies collide because gravity makes them collide. Even though the universe is expanding, that universe has stopped expanding in certain pockets. Let's say between us and Andromeda, the universe is not expanding. There are certain pockets of space where gravity has stopped the expansion, and in fact things have reversed and things are colliding. Okay? Yeah, so it's not clear when people talk about multiple universes, it's not clear that those are going to collide. It's not clear what separates them. There's talk of domain walls that separate them. They don't necessarily communicate with each other. No, there wouldn't be collisions between galaxies and parallel universes. That would defeat calling them parallel universes, because they really have to be out of communication with each other. I saw a hand up here. Yes, please.
Could you comment more on dark matter? Because it's used to, it's invoked to explain the rate of rotation of galaxies. Also, invoked to explain the rate of expansion in the universe.
That's correct.
Which I think
Right.
have to have an opposite sign.
Right. No, so there are two different things here. One is called dark matter, one's called dark energy. So they're both dark in the sense we're in the dark about them. So there are some Nobel Prizes to be won there in the future. But so we don't know the exact composition of dark matter. We know its demographics, though. We know how much is present in galaxies. And dark matter actually even plays a role in this expansion. People thought early on that if there's dark matter present, then the expansion rate of the universe should be slowing down over time. And in fact, if you look back at the history of the universe expansion, just by looking out in space, you can look back in time. The universe, in fact, was expanding faster, then started slowing down. But one of the remarkable discoveries in the last 5 or 10 years is that that's been speeding up again. So that requires something, exactly as you said, has to behave opposite to dark matter, has to have a pushing out, a pressure. And that we're equally ignorant about, and we call that dark energy. And I used to joke to say that gravity sucks, but dark energy is truly repulsive. But both of those things are here to stay. I mean, the evidence is very clear that, in fact, there was a recent Nobel Prize given out for the discovery of dark energy. Okay, let me take a question over there, and I'll come back to you.
I have a very simple question. So all these pictures of galaxies, are they optical pictures?
Many of them are optical pictures, but one can take pictures in radio waves, in gamma rays. Such pictures do exist. In fact, slipped in among my pictures, there were some X-ray pictures, there were some infrared pictures, and many of them were optical or ultraviolet pictures.
If that is the case, you said they were like thousands of light years away. Means the picture that we have, is it as old as, we don't know if that even exists now?
Absolutely right. We don't know if they exist now. In fact, we have no choice but to look into the past. In fact, when you're seeing me and I'm seeing you in the past. It so happens that that past is only a fraction of a second in the past, which is a small fraction of human lifetime. In this case, the distances are big enough that it's much larger than human lifetime, much larger than our civilization's lifetime. So looking into the past is nothing new, and that's imposed on us by the finite speed of light. There is no such thing as the present, in some sense. You can only sense the past. And how far in the past depends on how far away. So those two things are coupled. Space and time are coupled along something called a light cone. So as you look out in space, you're looking back in time proportionate to the distance you're looking out to. Okay. Yes, I haven't heard a question from you, please.
So if you said like if there was a pattern that it slows, like it speeds up and then it goes down, would it be like the same thing, or would the pattern change?
What was the question?
So the question is, as the universe expands, you said the pattern expands and then shrinks and then expands again. It doesn't shrink. The rate of expansion slows down a little bit. It's still expanding, but just not as rapidly as before, and now it's speeding up again. Yes, to answer your question, you asked, does the pattern of galaxies stay the same? On large scales, yes, it does. On very large scales, it does. On small scales, it doesn't. Galaxies, there are pockets of the universe where the expansion has stopped. Gravity has taken over, there's reorganization going on there. Those patterns are indeed changing. So on very large scales, the overall distribution pattern of galaxies is staying the same.
One or two more questions.
One, two, okay. Way at the back there, then I'll come back to you, okay?
I have two questions. One is that do you think universe is like finite or infinite?
So if you'd asked me this question a few years ago, whether the universe is finite or infinite, I would have said it's infinite. But now there's talk of multiverses, so that automatically means there has to be some limit to our universe. So you might ask, how far away is that limit? How far away is the nearest domain wall? I can only give you a guess at that. We can see out to 14 billion light years. You multiply that by 10 to the power 50, that might give us a rough sense of where the nearest domain wall is. So yes, if there are domain walls, they're very far away, very likely. And your second question?
The second question is, if you use like mass and energy together and consider as energy of the net energy of the universe, do you think that is zero or non-zero?
That is a very good question. The question is there conservation of mass and energy, or is the sum zero or non-zero? The sum is almost certainly non-zero. In fact, if the universe is infinite, that sum is infinite. But how dark energy behaves as the universe expands, the so-called equation of state of dark energy. We know how an ideal gas behaves as you expand or contract it. How dark energy behaves as we expand, as the universe expands, is one of those big burning questions about trying to characterize dark energy. It's something called the equation of state of dark energy, and there's a so-called quintessence theory of dark energy that tries to address this question, but it has some variables that one can try to pin down. I see absolutely burning questions in the.
I think we should close now.
Okay, all right. If we can carry on this discussion over lunch, if people are coming to lunch, that would be great.
All right, so let's thank our speaker. Thank you very much, Raja.